Hi everyone. This is going to be a lesson about vector spaces for linear algebra. Before we start, I want to say a couple of things about where this lesson fits in with the big picture, like with the overall course. So we've been following along with this recommended textbook, Linear Algebra by Lay, and McDonald. And we're at the point in the course where we're skipping around through different chapters. So the most recent things we did were determinants. That's in chapter 3 of this book. And now we're going to be doing some material from vector spaces, which is chapter 4. And if you're keeping track of textbook sections, I'll tell you this lesson is going to cover some of 4.1, 4.2, and 4.3. Not every detail, but it's going to mix those three together. And really what vector spaces as a lesson is all about is it's going to generalize some of the things that we've already seen before, such as subspaces and bases. We saw those in chapter 2. Okay, so it fits in. You'll see what I mean when I say that it generalizes those concepts. In math, a lot of times we like to learn about something in a specific sense and then sort of take a step back and see that concept in a broader sense. And we're going to see that there are subspaces of things other than Rn. Because earlier we only did subspaces of Rn. So that's probably enough of my introduction. Let's go ahead and get started and see what this is all about. All right, so vector spaces. This is probably one of my favorite sections in the course. I'll tell you that this lesson generalizes or expands on material we learned earlier about subspaces, bases, etc. Remember, we talk about the basis of a subspace, but when you're talking about them in like the plural sense, when you're talking about more than one of them, the plural form of basis is bases. All right, so what we're going to do is we're going to jump right into the definition of a vector space, because you might be wondering, what is a vector space? And this is a pretty long definition. So let's get started. It's not like a very difficult definition, but it's just a long one. So a vector space is a non-empty set V of objects called vectors on which are defined two operations called addition and multiplication by scalars. I should say multiplication by scalars. Scalars in this context meaning real numbers. Oh, this keeps going. It keeps going. A vector space is a non-empty set V of objects called vectors on which are defined two operations called addition and multiplication by scalars, such that the following properties are satisfied. There's going to be a list of properties. So what have we got so far? Just before we list some properties. It seems pretty vague, doesn't it? It's a set of objects. Well, any set could be, any non-empty set could be called a set of objects. So we probably could have phrased this differently. But anyway, it's a set where the elements of the set are called vectors. Whatever they might be, we call them vectors if they are elements of a vector space. And then on this space, there are two operations defined called addition and multiplication by scalars. Now, I'm going to warn you, it might not be addition in the traditional sense, and it might not be multiplication by scalars in the traditional sense. You'll see what I mean by that. Following properties. So it's going to be a certain type of set with two operations defined on it that satisfy some properties. For any vectors, u, v, and w in V, and for all scalars, C and D. All right, we need a list of properties. So a vector space is a special kind of set with special kinds of operations. It's not just any set. It's not just any kinds of operations. They have to interact according to a set of properties. And I said this definition is not very hard, but it is a long definition. Well, I'll tell you right now, there are going to be 10 properties. There are 10 properties of a vector space. So we're going to number them. First property, you could call these things the requirements, the things that are required for a set to be a vector space. Okay, requirement 1, the sum of U and V denoted U plus V is in V. All right, so we said that there was going to be an operation called addition, and here we are saying that it is denoted with this symbol. We know this symbol because we use this in math for addition. Well, we use it in math for this kind of addition also. And we're saying that when you add two elements of a vector space, the result, the sum, is still in the vector space. So we say it's closed under addition. Property 2. U plus V is equal to V plus U. Now you might be saying, isn't that a property that we already know? Well, if you're thinking that, I'll tell you, this is a property that we know for Rn. This set might not be Rn. And these objects might not be column vectors. They might be something else. So two elements of a vector space are being added, and we're saying that they can be added in the other order. They might not be column vectors, even though we're using this vector notation. So this is not a property that we automatically know already. This is a property that some sets have and some sets don't. So if it's going to be a vector space, it has to have that property. The next one, oh, by the way, that's saying that addition is commutative. The next one is saying that addition is associative, which says that we can rearrange parentheses, which, rearrange parentheses, what does that mean? What this really means is that we can rearrange the order in which these operations are done. You can add U plus V first, or you can add V plus W first. And either way, these three vectors add up to the same thing. Property number 4. There exists a zero vector denoted by 0 with the vector symbol above it in V, such that v plus the 0 vector equals v. So the set that we're talking about has to contain an element that acts as a 0 vector so that when you add it to any vector v, it doesn't change v. Adding 0 doesn't change the vector that you started with. These seem like reasonable properties to look for in a set. For every vector u in V, there is a vector negative u in V, such that u plus negative u equals the 0 vector. That's a nice property to have. That means for every vector that's in your set, you have to have the negative version of that vector in the set. This is starting to seem like a vector space probably needs to have a lot of things in it. Think about this. Could you have a vector space that only has like 3 entries, 3 elements? I mean, it says that when you add 2 elements together, the sum has to be in the vector space. So that right there seems like if you have 2 elements, then you add them together, you have to have the sum of them, and then you have to take that and be able to add it to any vector and have the sum of that also be in here. And then you take that and add it to these, and the sum of that also has to be in here. So it seems like you have to have a lot of elements. Every element has to have a negative version of itself. You could call this the additive inverse. A lot of times we talk about the multiplicative inverse. Multiplicative inverse, that when you multiply them together, you get something like an identity, a multiplicative identity. Well, here, you take a number and you add its additive inverse, and you get the 0 vector, which could be thought of as kind of like an identity for addition. Also, when you add the 0 vector, it doesn't change anything. Just like when you multiply by the multiplicative identity, it doesn't change. Anyway, I'm getting a little bit off topic. We have 10 of these. So the first 5 seem like they were properties about how addition works in a vector space. The definition said that there's addition and another operation called scalar multiplication, and the rest of the properties are going to be about how scalar multiplication works. So the scalar multiple of u by c, denoted cu, is in V. So when you multiply any vector by any real number, the result needs to also be in your set. So yeah, vector spaces seem like they probably have a lot of elements. Next property is sort of a scalar multiplication distributive property from the left, saying that when you multiply a sum of 2 vectors by a scalar, that you can distribute across the parentheses. Next, we have a different kind of distributive property. If you're adding 2 scalars in parentheses and multiplying by a vector, you can distribute across the parentheses in that way. Number 9 says, we've seen properties like this before. So if you're doing what's in the parentheses first, as order of operations says, this says that multiplying the scalar d times u and then multiplying by c is the same as just multiplying cd together first and then multiplying them by u. And I said there were going to be a total of 10 properties. The 10th property is that 1 times u equals u. The scalar 1, when you multiply it times a vector, does not change the vector. All right, so if these properties look familiar to you, it's probably because you're thinking, these are properties that we usually have in linear algebra, right? Usually we can add vectors in either order, and we have the associative property of vectors, and scalar multiplication usually works this way. Well, you're probably thinking about the things you know about vectors in Rn. But this definition didn't say anything about Rn, and it didn't say that these objects have to be column vectors with, n real numbers in them. So in fact, this definition includes Rn, but it could also include other things as well. So let's start seeing some examples of vector spaces. I think we need to see some examples. And example 1 of a vector space is that Rn is a vector space. And I'm going to say it is the most commonly used. And everything that we've done in this course so far has basically been using this vector space. We've been doing linear algebra in Rn. We've been using real numbers. We've been using column vectors. We learned about how to add vectors. We learned about how to do scalar multiplication. And we learned all of that in this vector space, Rn. But now's the time to take a step back and say, is there a different way to do things? Are there other types of sets that kind of share some of these behaviors of Rn? So in a way, the other examples that I'm about to show you of vector spaces, they're going to look pretty different, but they share some of the same kind of structure as Rn because they have all 10 of those properties, and those were properties that we usually associate with Rn. So example 1 was that. Example 2 of a vector space. It's going to seem a little different, but I want to show you one that's a little different. For n greater than or equal to 0, let P with a little n down here be the set of all polynomials of degree at most n, such that the coefficients and variables when I say polynomials, I guess I should technically say in one variable. Polynomials with one variable. Polynomials of degree at most n such that the coefficients and variable are in R. Then Pn is a vector space sometimes written as this fancy looking P with the n down here. I would put the n down at the bottom, not up top like an exponent. It's a subscript, not a superscript. All right, I claim that this is a vector space, and in order for me to show you that this is a vector space, I should explain to you, if this is a set, what are the vectors? How does addition work? How does scalar multiplication work? And are we getting all 10 of the properties? So example 2 we're going to discuss here in a little more detail. First of all, in example 2, what are the vectors? Well, vectors are supposed to be the elements or objects. So each object, in parentheses I'll say vector, in this set is a polynomial of the form, I'm going to call it P of t equals a sub 0 plus a sub 1 t plus a sub 2 t squared plus dot dot dot. We don't really know how big n is, but it goes up to an t to the n. And that is what a vector is in this vector space. It is a polynomial. I think that this vector space Pn has a lot of polynomials in it, but they all fit this form. So we could talk about the vector space P2, P3, P4, whichever one we're talking about. The vectors that it consists of, each one of them is a polynomial. So we're not using the word vector the way that we've used it earlier in the semester. We're using the word vector in a broader sense. In this vector space, vectors look like this. In some other vector space, vectors might look like something else. But in this one, this is a vector. Let's talk about how addition works in this vector space. Really, I probably could have talked about addition and scalar multiplication above when I first said this is a vector space, but we're just going to talk about it here. So if you're given, we want to say if you're given two vectors, how do you add them together? So let's say we're given, well, let's say one of them is P of t. We need a second one so that we can add them together. So we're going to have one called Q of t. Same variable, but possibly it might have different coefficients. I mean, these might be the same coefficients for all we know, but that would be a big coincidence. All right, given P of t and Q of t, we define P plus Q by, we're going to define addition in this vector space to be just addition of polynomials, that when you add P plus Q, you get a new polynomial, don't you? And you can do this just by adding the coefficients, can't you? Like a sub 0 plus b sub 0 plus a sub 1 plus b sub 1 t plus a2b plus b2 t squared plus dot 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 all the way up to an plus bn t to the n. This is how addition works in this vector space. When you add two polynomials, you get something like this. I think that I can see that property 1 is satisfied. We'll talk about that in a minute. But we need to say, how does scalar multiplication work in this vector space? Can we multiply a polynomial by a scalar? Sure, yeah, why not? So let's say we're given a scalar, c, from the set of real numbers. We define c times p by c times p of t equals, you just multiply it by all the terms. Okay, so just multiply c by all the coefficients. That's how scalar multiplication works in this vector space. Now, do all 10 properties hold? I told you that this is a vector space, so all 10 properties had better hold. Otherwise, I'm lying to you. I don't think we're going to go through the steps of verifying all 10 of them, but I just want to discuss some of them. First of all, one of the conditions for this to be a vector space is that it has to be a set. Well, it is a set. Does it have two operations called addition and multiplication by scalars? Yes, we just described them. So now it also needs to have 10 properties, and I'm going to say all 10 properties hold. They are the requirements for being a vector space. And I'll discuss some of them. So property number 1, the sum of two polynomials is always a polynomial. That's important because we're not just saying that you can add any two polynomials together. What we're saying is that when you add them together, the result is still a polynomial. You're never going to add two polynomials and get some different kind of object. Like, you're never going to add two polynomials and suddenly you have a trig function, or add two polynomials and suddenly you have a matrix, right? They're not going to suddenly turn into some other kind of object. When you add two polynomials, the sum is still a polynomial, so it is still in this set. Oh, I guess I should say that when you add two polynomials of degree at most n, the result is also going to have degree at most n. Right? You add something of degree 2 and something of degree 2, the degree is still 2. The degree does not increase when you add two polynomials. Oh, you know what? I said I wasn't going to go through all of them, so let's just say ... I wanted to talk about number 4. Okay, we're skipping some of them. But number 4, does there exist a zero vector in this space? This actually does warrant some discussion. So the zero polynomial. The zero polynomial, p of t equals 0. So this is like the constant function, p of t equals 0. No matter what value of t you plug in, the result is always 0. It is included in Pn, even though technically its degree is undefined. Yeah, this is kind of a subtle thing, but a while back when you had some algebra class and you learned what polynomials were, you may have had a definition and it may have said something like the degree of a non-zero polynomial is defined as ... But usually we talk about the degree of a non-zero polynomial. What is the degree of a zero polynomial? Technically, it's undefined. We are including it in this set so that it will be a vector space. It has to be included in the set in order for this to be a vector space. If you're following along with the textbook that we're using, I'll just say, well, this is mentioned on page 194 if you'd like to see more details. It's kind of a little subtlety, but we have to include the zero polynomial in order for this to be a vector space. That's okay, though. Even though its degree is undefined, it kind of feels like it belongs in this set, because we're taking things of degree n, at most degree n, so you have everything that's degree n or less, and it kind of feels like this belongs here, doesn't it? Number 5, the negative of a polynomial is always a polynomial. So you always have a negative version of anything. and I'll just say, etc. You can go through the rest of the 10 if you'd like, and you'll see that they all work. So what we've done is we've said that this Pn is a vector space, and I think a little later I'm going to do an example problem that takes place in this vector space. But I think I want to show you one more example first of another vector space. So far, the two that we've seen are Rn, which is the set of all column vectors with n entries. We've seen Pn, which is the set of all polynomials of degree at most n. Example 3 of a vector space. Let R m by n be the set of all m by n matrices with entries in R. Addition and scalar multiplication are defined as they were earlier in the semester. Then R m by n is a vector space. Pretty cool, pretty cool. So we could talk about the set of all matrices that are all the same size. As long as the matrices are the same size, we can add them together. We have negative versions of matrices. We have scalar multiples times matrices. We have all 10 properties. You could go through all 10 and verify that they do work. Some of them are properties that work because we specifically said those properties for matrices. Let's see. Let's look at some of the properties in particular. Does property 10 work? So what is property 10 saying? It says 1 times a vector equals that vector. In this vector space, what is a vector? A vector would be an object in this set. So in this space, a vector is an m by n matrix. I know that seems a little weird. We're using the word vector to talk about polynomials and matrices, but we're kind of broadening the usage of that word vector. Anyway, yeah, so 1 times a matrix is, we're doing a scalar multiple of 1 times a matrix. Yes, property 10 does work. What about property 4? What is the 0 vector? Is it like a column vector? No, it can't be a column vector. So for property 4, in this vector space, the 0 vector is the m by n 0 matrix. Because any element of this set has to be an m by n matrix. And this works because if you add this 0 matrix to any other matrix, it's just like adding 0. It doesn't change it, right? And, you know, we leave it in this notation, by the way. If you want to talk about R 2 by 3, you just write it as 2 by 3. You don't multiply them out and say 6. So R 2 by 3, R 3 by 4, whatever size matrices we're talking about, R 2 by 2. And yeah, it is a vector space. Now, what can we do with vector spaces? I mean, example 1 was Rn, and we've done a lot of linear algebra in Rn. What can we do with other vector spaces? So I have a definition. Definition: a subspace of a vector space V is a subset H of V such that there are three requirements for being a subspace. Number one, the zero vector of V is in H. Number two, for every U and V in H, we have U plus V in H, using the for every symbol. For every vector U and for every vector V in the set H, we have U plus V is also in H. For every U in H and C in R, we have CU is in H. This is the same definition of subspace that we've seen before, isn't it? Almost. This is almost the exact same definition of subspace that we've seen. The difference is that when we saw it previously in the semester, it said a subspace of Rn. It said a subspace of Rn is a subset of Rn, such that, and then it had these properties. Well, we're broadening our perspective right now, and we're saying that, in fact, you could have a subspace of any vector space, not just Rn. But the definition, the requirements are the same. A couple of quick remarks. So you think about like example 2 or example 3 of vector spaces. We could talk about subspaces of them. But a couple of quick remarks before we do anything like that. Number one, V, the vector space itself, is a subspace of V. Now, I think we proved that for Rn. I think we showed that Rn is a subspace of Rn. I mean, clearly these, I guess I shouldn't say clearly, but I'll just tell you that every set is a subset of itself. So that part we already have. V is a subset of V by definition of subset. But yeah, it does contain the zero vector, and it does have these properties. Remark number 2, every subspace H of V is itself a vector space. Now, that might be a little bit less obvious. That's less, Can we see that that's true? Well, I know that a subspace is a subset of V, so I know it's a subset, that we have that much. Do we know that we have all three properties? I guess it makes sense that if it has these three properties, it makes sense that it has the zero vector. That means that it has property 4 of a vector space. Property 2 over here looks like it's telling me that we have property 1 of a vector space. But in fact, you can verify that you do get all 10 properties. From being a subset and having these 3, you actually get all 10. So that's cool. So that means that subspaces can help us define more vector spaces than just the 3 examples we had. think we're ready to do, let's do an example problem. I'm going to walk us through this. This is all still pretty new to us. So let H be the set of all polynomials, lowercase p, in Pn such that P of 0 equals 0. Is H a subspace of Pn? Let's talk about this. Pn, we know, is a vector space. I'm choosing some of the polynomials in Pn. I'm choosing the ones that have P of 0 equal to 0. I don't know, I guess visually or graphically you could say they're the ones that pass through the origin. But yeah, they send 0 to 0. Is that set of polynomials a subspace? It would have to satisfy the 3 conditions that we just wrote above in the definition of subspace. I'm going to say first, note that H is a subset of Pn. We can see that everything that's in H is in Pn, because everything that's in H is a polynomial. It's just a certain kind of polynomial. What kind of polynomials does H include? Let's think about this. Before we actually are like proving anything, I just want us to think about this. What kind of polynomials does H include? How about H includes, I'm just going to give an example of one. 3t squared minus 5t cubed plus t. Can you see that that is in H? Well, I guess I'm assuming that n is 3 or more. I guess by making this t cubed, I'm kind of assuming that n is larger than that or equal to that. But yeah, you know, suppose it is. Suppose n is 4, 5, 6, something like that. H includes this because I can see from the way I wrote this polynomial that P of 0 would be 0. It does not include something like t squared plus 1. Because in that polynomial, I can see that P of 0 is not equal to 0. So this is me just doing a little bit of scratch work, trying to understand what this set is all about. H includes some polynomials and does not include others. Let's start checking for the 3 conditions of being a subspace. Because we're trying to answer yes or no, is it a subspace? So we'll check condition number 1. Is the 0 vector of Pn in H? I'm going to say the 0 polynomial, P of t equals 0, has P of 0 equals 0. So it is in H. That's it for condition 1. Yes, condition 1 is satisfied. Condition 1 of being a subspace. Does it have the other 2 properties, though? The other 2 conditions? Well, we need to have 2 things and add them together. So let u of t and v of t be 2 polynomials in H is U of t plus V of t also in H. We need to know that it's in H in order for this condition of a subspace to work. In other words, what would it mean for the two of them to be in H? Well, to be in H, it has to be a polynomial that has, it has to be a polynomial that sends 0 to 0. So, in other words, does this equal 0? Well, when I add them together, U plus V is U of 0 plus V of 0, right? So yes, this is going to be 0 plus 0. So it does work out. So condition 2 holds. We've got 2 out of 3. Let's check condition 3 and find out, is this one going to pass or fail? Let U of t be an element of H, and let C be a scalar. We need to see if when you multiply the scalar times the vector, the multiplying C times this polynomial, is it still in H? To be in H, it has to send 0 to 0. So C times U of 0, does this equal 0? Yes, this does equal 0 because it's C times 0. Any real number times 0 always equals 0. So C times U of t is in H. And we can say in conclusion, yes, H is a subspace of Pn. So we just defined a new subspace of this vector space, and above I said that every subspace is itself a vector space, meaning that it has all 10 properties, which I said above as a fact, so we don't have to like go through and verify all 10, but I guess you could say that we know some more vector spaces now, right? Like, take this subspace of P5. Take this subspace of P10. Whatever you want, you've got yourself some more vector space examples. So remember, in general, a subspace is a special kind of subset. And I guess a vector space is a special kind of set that has a bunch of nice properties that we like to have in linear algebra. Now, it feels like we could probably do some of the other things that we've done in Rn, but apply them to vector spaces in general now. What have we done in Rn that you think we might be able to do with some of these other spaces? Subspaces, that was one thing. But what else have we done with Rn? How about linear combinations? We talked about linear combinations of vectors in Rn. Now we're going to do that for any vector space. So given vectors, let's call them v1, v2, etc., up to vp, from a vector space. A linear combination is a sum of scalar multiples. multiples of the vectors. All right, it says a linear combination is a sum of scalar multiples of the vectors. So that would be something like C1v1 plus C2v2 all the way up to CPvp. When we talked about linear combinations earlier in the semester, we also introduced the word span, and we can talk about span in this sense also. So the span of a bunch of vectors is the set of all linear combinations. Of V1 through VP. What I'm getting at here is that a lot of the things that we've done in this course for Rn can also be done for other vector spaces. We can talk about subspaces. We could talk about linear combinations. We could talk about linear independence. I guess since we spoke about subspaces, we could talk about a basis for this subspace. What is a basis for this subspace? You know, if we talk about the basis, we could say how many elements are in the basis. So yeah, there's a lot of stuff that we've done in this course for Rn that we can now do in these more abstract vector spaces, where the elements might be something totally different. They might be polynomials, they might be matrices, they might be something else. Some other kinds of functions. It could be a set of functions, it could be a set of sets. There are lots of possible vector spaces. So a couple of things I want to say here. Note, the span of a bunch of vectors is always a subspace of the vector space it came from V. We said this fact earlier in the semester for Rn. Do you remember that? We said this as when we first talked about subspaces, I guess. And we said, you know, example of a subspace of Rn is you take the span of some vectors. And now we're saying that this also applies to any vector space. For example, sorry, I need to get these pages straight on my desk. For example, let H equal the span of P and Q, which is a subset of P3, where P of T equals this polynomial and Q of T equals this polynomial. See what we're doing here? We've got P3, which is the vector space of all polynomials of degree at most 3. I've taken two elements of it, two vectors from P3. It's this polynomial, degree is less than or equal to 3. This polynomial, degree is less than or equal to 3. I said, let's take the span of P and Q. That's the set of all linear combinations of P and Q. And I call that H. And this is a subspace of P3. So that's an example of a subspace of a vector space. H includes any linear combination of P and Q. And you could try out some linear combinations of P and Q, but like in general, any one would look like C1P plus C2Q. Where C1 and C2 are scalars. I guess you could also write it as C1 3t plus 5 plus C2 t squared plus 1, because that's what P and Q are. For example, I'll give you an example of one thing that is in H. I'll give it another name. Since we already used P and we already used Q, I'm going to call this one R. The polynomial t squared plus 3t plus 6 is in H. Do you see how I got this polynomial as a linear combination of the other two? Do you see what values of C1 and C2 we would have to have? Yeah, I got this one pretty simply. I said, what if C1 is 1 and C2 is 1? Then they add up to give me this. This is from C1 equals 1 and C2 equals 1. But you could pick other ones too. You could pick, pick your two favorite numbers. Pick your two favorite real numbers. They could be the same if you want. You could have some of them be 0 if you want. But yeah, when you do this, you're going to get some polynomial that is in H. That's what H consists of. Here's a question. I'm looking at that subspace that we wrote above. Wait, let me move the page up just a moment. I'm looking at span of P comma Q. And when I see span of P comma Q, I'm thinking to myself, do you think P and Q form a basis for this subspace? Well, what is it? What are the requirements to be a basis? I mean, I guess the span, like P and Q have to span H, and they do span H. The other requirement, which I'll write down here as a question, are these two polynomials linearly independent? I know it seems weird, right? We're asking about linear independence, but the objects that we're considering, they're not vectors in the traditional sense. They're vectors in this more abstract sense. Well, I'm going to say yes, because neither is a scalar multiple of the other. Which was a result that we said earlier in the semester. So the set consisting of just P and Q is a basis for the subspace H. Oh, here's another question. What is a basis for Pn? What do you think a basis for Pn would be? I'd like you to think about this question for a minute. You could pause the video if you'd like. See if you can come up with a basis for Pn. So, you probably know from our discussion of bases earlier in the semester that there could be more than one correct answer. There might be one answer that is sort of the simplest and nicest answer, but there could be other equivalent ones. So I'm going to write what I think is the nice basis for it, and that is going to be 1t squared t cubed, etc., all the way up to t to the n. That forms a nice basis for Pn, because we're trying to get all polynomials of degree at most n. So take linear combinations of these elements. Doesn't that work out perfectly? Linear combinations of these elements get you polynomials of degree at most n. I'm going to tell you that the details of this are in the textbook, and it's discussed in section 4.3, bottom of page 211. Because in this lesson today, we're kind of covering multiple sections from this book. So there's just a couple of things that I'm pointing you to in the text. All right, so that answers that. I'll tell you, we define dimension to be the number of elements in a basis. So the dimension of H, when I said H, I'm still talking about this example above, which was the span of these two things, and we said that they were linearly independent and they form a basis for H. So the dimension of H is 2, because we demonstrated a basis that has 2 elements. There could be other ways to write a basis for that particular subspace, but we have those two as kind of our basis representatives. And what's the dimension of Pn? Well, how many elements are in our basis? We have 1 for each exponent, going from an exponent of 1, 2, 3, 4, all the way up to n. But we also have this thing here. This is also a polynomial. This is also a basis element. So altogether, the dimension is n plus 1. You can see that here. You could write out a basis for P5 if you want. You'll see that it has 6 elements. So I have a couple of questions that I'd like you to try. I'm going to be moving some of this away, so I'll give you just a moment in case you're still copying any of this. I think I'll probably just go to a fresh sheet of paper for this next question. So I'm going to ask you a question about vector spaces, and it's going to have 3 parts. Part A, find a basis for R 2 by 2, the vector space of all 2 by 2 matrices. Part B, what is dimension of R 2 by 2? And part C, I'd like you to guess a general formula for the dimension of R m by n. So I'd like you to pause the video, take a few minutes, and try to do all 3 of these. So for part A, we need a basis. So I'm thinking, what kinds of elements of R2 by 2 do I need so that when I take linear combinations of them, I wind up getting all 2 by 2 matrices? And here's the basis I came up with. Well, whatever you wrote, it should be a set of 2 by 2 matrices, right? Whatever alleged basis we have, it must be a set of 2 by 2 matrices. And I claim that this is a basis for R2 by 2. There are other answers that are also correct. I mean, really what you would have to do is come up with 4 2 by 2 matrices that are linearly independent of each other and that span the entire set. This is the simplest example of a basis for this problem. I mean, if you replace all these 1s with 2s, it also works. If you replace this one with a 2 and replace this one with a 7, it also works. But this is the simplest way that you could write a basis for this one. And you can see that if you did linear, like any linear combination of these 4 things, you're going to get any 2 by 2 matrix you want. So that's a basis. You know, just for example, I'm going to make up a matrix here. I'm going to try to pick 4 random real numbers off the top of my head. Pi, -2, 0, and 0.7. All right, those are just the first 4 numbers that came into my mind. This is an element of R2 by 2. Can I write it as a linear combination of these basis elements? Yeah, just do pi times the first one plus -2 times the second one plus 0 times the third one plus 0.7 times the fourth one. So any 2 by 2 matrix can be written as a linear combination of these basis elements, and you can see that they are linearly independent. So the dimension of R2 by 2, it must be 4 because we demonstrated a basis that has 4 elements in it. You can't remove any of those. You can't trim this down to be 3 because if you remove one, then you're losing too much information. You need all 4 to span the set. So what do you think? We want to guess a general formula for the dimension of m by n. Well, I didn't really give you a lot to go off of. We only did this one example, but for the 2 by 2 case, we got a dimension of 4. So in fact, the guess that I was looking for, and in fact, the correct answer is mn. That if you had the space of all 3 by 2 matrices, you would need 6 basis elements. If you had the space of all 4 by 5 matrices, you would need 20 basis elements. And your basis elements could look kind of like these. They could be mostly zeros and just have 1s in the appropriate places. So that's a nice formula. It seems to kind of go with what we know about, like when we talked about Rn. Here's a little side note. Notice that when we've talked about Rn in this course, doesn't that really just equal Rn by 1? So I guess the idea of us talking about matrices, you know, vectors, column vectors are just a matrix that has 1 column. So So this new formula is consistent with what we've said before, which is that the dimension of Rn equals n. I'm just showing you that these two formulas, they don't contradict each other. Okay, so I have another question for you. This one is just going to have one part. Is the set, I'm going to give you a set of 3 matrices. Is this set linearly independent or dependent? And I'm going to say, prove your answer. So I'd like you to pause the video, try this for a few minutes. You need to answer the question and prove your answer. All right, so what I was hoping you would notice is, well, first, how do we approach this problem? How do you usually approach questions of, is a set linearly independent or not? Maybe go back and think about, what if I gave you a question a few weeks ago where I gave you a set of vectors and asked you, are they linearly independent? What it really comes down to is, does this, going back to the definition of linear independence, does this only have the trivial solution? That's really what this is asking. If you went back to the definition of linearly independent. I know it has at least the trivial solution, C1, C2, and C3 all being 0. But are there any other solutions? That's the question. Let's try to work with this. What can we do with this? Well, does the left-hand side equal the right-hand side? What would C1, C2, C3 have to be? How about this? Put the scalars in. Like, we're doing scalar multiplication, so just go ahead and do the scalar multiplication. Bring the scalars inside. 3C3, 5C3, 0, and 2C3. We want this to add up to 0, 0, 0, 0. That is the 0 vector in this vector space. What is the left-hand side? We can add these together, can't we? Add up all 3 of these, and you should get C1 plus 3C3. Over here, I guess you get C1 plus C2 plus 5C3. Over here, you get what? 0 plus 0 plus 0. So just a 0 over here. And then over here, C2 plus 2C3. And it's still the same question as above. Does this equation only have the trivial solution? Well, in order for 2 matrices of the same size to be equal to each other, they have to have all of the corresponding entries be equal to each other. C1 plus 3C3 would have to equal 0. This other thing would have to equal 0. This thing would have to equal 0. I can tell that the entry in the lower left already equals 0, so that doesn't even... There's no work to do for that one. But the other 3, do they equal 0 at the same time? That is what we call a system of equations, right? We've got three things that we would like to all equal 0 at the same time. Let me move this page up. The corresponding entries need to match up. So we get a system of equations we're trying to solve. We're looking to see if there are any non-trivial solutions. So I always say that a lot of questions in linear algebra can be turned into solving a system and doing row reduction. So let's do it. C1, C2, and C3 are the unknowns. We take the coefficients, turn this into an augmented matrix. 1, 1, 5, 0, 0, 1, 2, 0. That's the augmented system. We can do row reduction, and we'll be able to solve and find out what C1, C2, and C3 are. I'm not going to write out all the details of the row reduction. We've done row reduction a lot this semester, but I wound up getting 1, 0, 3, 0, 1, 0, 3, 0, 0, 1, 2, 0. And then I went one step further. I saw that two rows were the same, so I guess I added a -1 times row 1 to row 2 and something like that, and got... Also, I interchanged rows to put the row of all zeros at the bottom. All right, so I row reduced. What does this tell us? What do you think? What does this tell us? What does this column tell us in particular? C3 is a free variable. So that means that there are non-trivial solutions. As soon as you find a free variable, you know that there are infinitely many solutions, which means we have more than just the trivial solution. So we'll say the set is linearly dependent by the work shown above. I think it said to prove your answer, and I think that the work that we showed above is easy enough to read, and I think that that justifies why this answer must be true. All right, so that was a cool problem because it was about linear independence, but instead of working with vectors, we were working with 2x2 matrices. But in the end, it still turned out to be the same type of strategy that we would use for checking the linear independence of column vectors. All right, so we're going to be wrapping things up here. So what do you think? Vector spaces. I really like this section. You know, I think that every student of math has different preferences. You know, some students like things that are more applied math, like real-world problems, crunching numbers, and some students like things that are more abstract. This section was probably more abstract, right? And we were looking at generalization of Rn, and we were talking about addition and scalar multiplication as if they were something new to us, when really we kind of know how they work. Anyway, what I'll say is my own preference is I like both. I like applied math. I like abstract math. Pure math is what you could call it. And I'm kind of somewhere on the fence in the middle. But I'll tell you that if you like this kind of stuff, if you like this kind of abstract way of, you know, looking at things very generally, the class abstract algebra goes a little further in this direction. Vector spaces might be one of the kinds of objects that you look at in a class in abstract algebra. Then there are other types of objects you might look at in those classes, such as groups and rings and fields. You could look up some of that stuff on your own if you want, if you're a math major and you're curious, look up abstract algebra, see what that's all about. Anyway, we are here in linear algebra and we have some other topics that we need to discuss. So we're, in the part of the course where we're kind of jumping around to a few different topics. It's because in the first part of the course, we taught you a lot of the fundamentals, solving systems, understanding how to work with vectors and systems and matrices. The linear transformations was another big thing. And we learned about determinants and inverses. So we're at the point now where we can jump around and show you a bunch of different topics because you already understand the fundamentals. So the next lesson that you see from me is going to jump to the next chapter, and we're going to be kind of sampling different topics from throughout the book. All right, so that's it for today, and hope everybody's doing well. And yeah, stay tuned, and I'll see you next time.